Okay, guys, now let's talk about this new section that we're going to be teaching about. This part of the thermodynamics course will be about devices that move heat. That may sound boring at first, but actually, that is extremely practical and very relevant to modern engineering and engineering systems. So, in this module, we'll cover two closely related machines, which are heat pumps and refrigeration systems. So, these are basically the same machine. The only difference is what you care about. So, do you want something warm? That's a heat pump. Or do you want something cold? That's a refrigerator or air conditioner. And a heat pump can work as an air conditioner as well. So it's the same physics, the same cycle, just different purposes. So normally heat flows by itself from hot to cold. So a hot coffee cools down, a warm room loses heat to the cold outdoors, and a heat pump does the opposite. It moves heat from cold to hot. So this doesn't work by itself. This isn't free, so it requires work, usually electrical energy. So you could think of a heat pump as a heat elevator. Electricity is what powers that elevator. So electricity in form of work powers that elevator. So everyday examples in systems like this is that you use an heat pump to heat from cold outdoor air or the ground or the water and deliver that into your house in the winters. So yes, even cold air contains heat, and that idea is crucial and often misunderstood as well. So the reason that we are covering this is that it's an essential part of thermodynamics, and it's one of the most energy efficient heating technologies. So it's used everywhere in modern engineering. On the outside of our office at Rengang, we have a heat pump heating our office space. Yeah, let's continue with a basic understanding of heat pumps. When we talk about heat pumps, we talk about usually a vapor compression cycle. So we are going to talk about a vapor compression cycle. So this cycle represents one possible heat pump process, meaning that we're transporting heat from a low temperature to a high temperature. So from low to high, and it's important to mention this because heat does not do this naturally, as you know. So heat always wants to flow from hot to cold. So when we move the heat the other way, we have to add work. Usually in the form of electricity. So this isn't free, but it can be very efficient. So the key point is that the vapor compression cycle lets us take heat from something cold, like outdoor air, or the ground, or the water, and deliver that heat to something warmer, such as a building or the inside of your living room. And here's a really important thing to understand. This exact system can be used for different or two different purposes. If your goal is to heat the building or your house, we call it a heat pump. But if your goal is to cool something down in the summers, we call it a refrigeration system or an air conditioner. So physically, it's the same machine. The only difference is what we care about. So do we care about the heat we deliver or the heat we remove? The idea, the same process, but different purpose. So it's something we'll keep coming back to throughout the module. Heating, cooling. Our learning goals before we dive into the details. I want you guys to be clear about what you are expected to learn in this part of the thermodynamics course. First, the goal is to build a basic understanding of how heat pumps and basic understanding of how heat pumps work and when or where they are used in real life. That means that you should be able to explain in simple terms what a heat pump actually does, how it moves heat, and why the same technology can be used for both heating and cooling. Secondly, I want you guys to learn how to analyze heat pump processes. That's something that you should be able to do after you're finished with a thermodynamics course. That means that we'll look at the thermodynamic cycle step by step, how energy and work flow through the system, and how we describe the process using different thermodynamics concepts. So you won't just see equations and mathematics, you'll learn what they represent physically. And third, I want you to be able to work on and analyze and evaluate possible improvements to the heat points. Heat pumps. So in other words, what's the limits the performance of a heat pump can have? What changes could we make to make it more efficient? And why some improvements are possible and others are not. So this is where the thermodynamics part becomes an engineering tool for you guys. And also, of course, I want you to gain some familiarity with alternative heat pump processes. So the goal is not to make you expert in every cycle, but to give you a solid overview of things when talking about heat pumps. So the plan for us to reach those goals is that we'll start by looking at heat pumps in general. Here the focus will be the big pictures. We'll show you some diagrams and stuff. So we'll talk about what these systems do, how heating and cooling are two sides of the same idea. So this is where we're going to build intuition before getting more theoretical. Next, we're going to introduce the reversed Carnot cycle. This is an idealized theoretical cycle, so you'll never build a real machine that works exactly like this, and that's completely fine. The point of the reversed Carnot cycle is to show us the maximum possible performance and the fundamental limits imposed by the thermodynamics. After that, we'll move on to the vapor compression cycle. This is one of the most important parts of this section because this is the cycle used in real heat pumps. And we'll go through that step by step and connect the theory directly to the real machines. And then we will look at process alternatives. So here we can ask questions like, are there other ways to move heat? What changes if we modify parts of that cycle? And why are some designs more common than others and stuff like that. Then finally, we'll briefly introduce alternative cooling methods. So these approaches that don't necessarily use the standard vapor compression cycle, but still important to know something about. So by the end of this section, you should have both a solid foundation and a kind of a broader perspective on heat pumps. So now we can look at how a heat pump is used for heating. A heat pump works by extracting heat from the surroundings or from some other available heat source, and then deliver that heat at a higher temperature than the surroundings. So let's utilize another color here to not make you confused. So that would be in your living room, for example. So even though the environment may feel cold to us, it still contains thermal energy, and that is what the heat pump uses as a source. So cold doesn't mean no heat. So if we look at the diagram here, at the bottom we have the low temperature reservoir. There's a low temp reservoir. So that's the surroundings, for example, the outdoor air, the ground or water and stuff like that. So from this low temperature source, the heat or the heat pump absorbs heat, which we call Q0, so absorbs heat. So heat is being taken from the environment. In the middle, we have the heat pump itself. So this is the heat pump. To make this heat transfer possible, we must supply work to the system. So we have to supply work to the system, which is the heat pump. So this works usually comes from electricity. And it is what allows the heat pump to move the heat from a lower temperature from the outside air to a higher temperature, the inside of your living room air. So that's where the second law comes in. At the top, we have the high temperature reservoir or your living room. High temp or your living space. So here the heat pump delivers that heat, and that's labeled QH. Delivers heat. Because that's a higher temperature than the ambient temperature. So this is the heat that we actually use, for example, to heat a building or your house. So to summarize what's happening here, we extract from a cold source. So the summary here. Extract from extract heat from a cold source, and then we add work to the system. In form of electricity, often. And then we deliver a large amount of heat. At higher temperature. So that delivered heat is what we care about when we use a heat pump for heating. So this simple energy flow picture or diagram is the foundation for everything that will follow. So including efficiency, performance, and why heat pumps can be so effective. So this is a heat pump used for heating. But we can also use the same heat pump, the same physical hardware, for cooling or a refrigeration. So in cooling mode, if you will, the system extracts heat from something that is colder than the surroundings and then rejects that heat to the surroundings or to another available heat sink. So this is exactly what happens in a refrigerator, for example, or an air conditioning system. So again, this doesn't happen by itself. We need to supply some work. So let's walk through the diagram here. At the bottom, we have the low temperature region, labeled TL. So low temp region. That could represent the space we want to cool. So let's say that we have we're in the summertime now, and we want to cool the inside of our living room. So living room. So from this cold region, the system removes heat. QL removes heat. And the heat removal is the whole point of the cooling. In the middle, again, we supply work. We have to supply work. Just like before, this work usually comes from electricity and enables the heat transfer against the natural temperature direction. So at the top, we have the environment labeled, so that's outside of house. Labeled T0 here. So here the system rejects heat, labeled Q0, rejects heat to the surroundings, to the surroundings. So that includes the heat we removed from the cold space, QL, plus the work input, W. So that's why the air behind a refrigerator, for example, feels warm. So when we use the system for cooling, we care about QL, the heat removed from the cold space. We still need to add work, and the surroundings receive more heat than we removed from the cold side. So the same physics apply here. It's the same machine, just a different objective for the machine. So understanding this distinction between heating and cooling is crucial because it's going to determine how we define performance and what efficiency actually means in each case. Okay, I think you guys get the point. So let's move on to something that is called the reversed Carnot cycle. The reversed Carnot cycle is a reversible process logically. So that means it represents an ideal, perfectly efficient limit, not a real machine. So this is perfect. You can think of the reversed Carnot cycle as the Carnot power cycle just run backwards. So instead of producing work from heat, we now use work to move heat. So instead of producing work from heat, we now use work to move heat. And we move that heat from a temperature low to a temperature high. Let's write that as well. Usually. So if we go through the cycle step by step from process 1 to process 2, we have isentropic compression. That's from state 1 to state 2, where the working fluid undergoes isentropic compression. That means that the fluid is compressed. And pressure and temperature increase. So pressure and temperature increase. And there's no change in entropy. So this is an ideal compression, no losses, no friction, no heat transfer, no change in entropy. Then from process 2 to process 3, let's just separate these. We have isothermal compression. That's where temperature stays constant So the system rejects heat to the high temperature reservoir, and this rejected heat is what we could use for heating. So the heat rejection happens at a constant high temperature. At constant temperature. Then from state 3 to state 4, we have isentropic expansion. That's when the working fluid undergoes isentropic expansion. So during this step, pressure and temperature drop. So no heat is exchanged, and again, entropy remains constant. So this is the ideal expansion process. And then finally, from 4 to 1, we have isothermal expansion. Isothermal expansion. So in this step, the system absorbs heat from the low temperature reservoir. Absorbs heat from temperature low reservoir. And this is a constant low temperature. So this absorbed heat is the heat that we remove from the cold source. So the big picture takeaway here for the reversed Carnot cycle is that it consists of 2 isentropic. So that's 2 isentropic, worth keeping in mind, and 2 isothermal. All of these 4 are fully reversible, so that's why the cycle gives the maximum possible performance. So this is the maximum possible performance. But impossible to build. So this defines the upper limit, in a way, for heat pumps and refrigeration performance. So it gives us a kind of a benchmark to compare real systems against. So the real cycles in real life will always perform worse and never better than this. So if we look at the reverse Carnot cycle in a temperature entropy diagram together, this diagram shows the let's go through it's the temperature and the entropy here. So this diagram is very useful because here we can visually see the areas that represents energy. So what we see here is not geometry, it's physics. So if we go through the cycle step by step, following the arrows here, you see that it's reversed counterclockwise. You see the arrows pointing this way. So from process 1 to 2, the process is upwards here. That's isentropic compression. That means entropy stays constant, so the line goes straight upward. So during this step, the work is supplied to the system. Here's where pressure and temperature increase. Then from 2 to 3, that process from 2 to 3 here. Let's just take away that arrow. From 2 to 3, we have isothermal at a high temperature TH because the temperature is constant because the line here is horizontal, as you see. So the system rejects heat to the high temperature reservoir. So that rejected heat again is QH. Yeah, from 2 to 3. And then from 3 to 4, the system undergoes isentropic expansion from 3 to 4. So again, entropy stays constant. The line goes straight down. So during this process, pressure and temperature decrease. As you can see, no heat is exchanged and work is recovered internally in the ideal case here. Then finally, from 4 and until 1 again, the process is isothermal expansion. So at a low temperature TL here, the system absorbs heat from the low temperature reservoir, and the absorbed heat is labeled QL. So QL here. Okay, so this is the heat we remove from the cold source. Now let's interpret the areas in the diagram. The orange area represents QL, which is the heat absorbed from the low temperature reservoir. So let's just get rid of these things. So this is the heat absorbed from the low temperature reservoir. Then the blue area represents the minimum work input. That is required to drive the cycle. So altogether, the blue area plus the orange area gives the total heat delivered at the high temperature. So this is plus here equals total heat delivered. So visually, this is equal to this equals QH QL plus the work input. So the key takeaway here from this reverse Carnot cycle visually explained is that this is the absolute best performance a heat pump or air conditioner refrigerator can ever achieve. So it requires the minimum possible work, and it's fully reversible, and it sets an upper limit for the real systems that we make in real life. So real heat pumps will never need more work than this, and never less. So this diagram is our reference point when we later analyze real cycles and measure how close or far they are from the ideal case. Okay, the last thing that I'm going to talk about in this video is the maximum performance factor, or the coefficient of performance, or COP. So when I look on the back side of a heat pump mounted on a building wall, for example, you will see a COP. So we are still looking at a reversible process, meaning the reverse Carnot cycle. That's kind of important to remember because everything we derive here represents the ideal upper limit, not something real machines can beat. So if we just start with the energy balance, which is heat delivered at a high temperature, QH, equals QL plus work. So that consists of the heat taken from the low temperature source, QL, plus the work supplied to the system, W. So this is not a new idea, it's just conservation of energy. Then we can also rearrange stuff here. So the work input is equal to the QH minus QL. So that's just a rearranged energy balance. Then we can define the coefficient of performance, or COP, for the heat pump used for heating. So for heating, we care about how much useful heat we deliver compared to how much work we need to supply. So the COP for a heat pump is defined as COP equals QH divided by QH minus QL. That's the QH divided by the network input. Now comes the key idea here. So for a reversible heat pump, the work input is minimal. So that means that the COP reaches the maximum possible value. So the COP maximum is equal to QH divided by the minimum required work. So we can write that as, let's write it a little bit. QH like this. For the reversed cycle, this maximum COP can be written purely in terms of temperatures as well. So the maximum COP for a heat pump, so COP maximum for a heat pump equals QH divided by QH minus QL, or also TH divided by TH minus TL. So these temperatures must be absolute temperatures, meaning in Kelvin. Not degrees Celsius. So if you use Celsius here, that would be a completely, or give a completely wrong result. So this equation right here tells us something important. If the temperature difference TH minus TL is small, then like this, let's use another color here. if the difference in temperature here is very small, then you see what happens. The COP becomes very large. But if the temperature difference is large, the COP becomes smaller. So heat pumps work best when they don't have to lift heat very far in temperature. So that explains why low temperature heating systems, good insulation and mild climate conditions all lead to very efficient heat pump operations. Let's make a one-liner. Heat pump use line, it's connected to what we saw here. So heat pumps works best when not having to lift heat far in temperatures. So that's the connection here. So the reverse Carnot cycle gives us the maximum possible COP, the minimum possible work input, and a clear benchmark for the real heat pumps. So real systems will always have a lower COP than the things that we calculate by utilizing the Carnot cycle or reverse Carnot cycle. So that result will be a reference point when we later analyze real vapor compression heat pumps. Okay, I think that's enough for an introduction to the section, and we will get deeper into the details in the next videos. Okay, thank you guys for this one. I'll see you in the next one.